Sorry, there's one more thing I need to change on my computer. I hope. Yes, everything is fine now. All right.
Okay, great. So we're happy to have Francois Le Maitre talk about dense totipotent free groups in full groups.
All right. So thanks very much for the invitation, and sorry for being late. As I was explaining, I had a bit of technical problems. So all right. So this so in my lecture, I want to touch on a topic which is a bit different from what you've seen so far in this series of lectures. Namely, I want to focus on non-free actions. So you've seen that there are some very nice kinds of results where when you have two groups, you ask that they act freely on standard probability space and that they share the same orbits. And sometimes you can say that, for instance, the groups are isomorphic, or also you can put quantitative restrictions on the orbit equivalence and say interesting, meaningful things about these groups. But so here, so the focus will be different. And as I said, we'll be looking at non-free actions. And so the starting point will be the following theorem due to Gaboriau, which says that if you have a PMP equivalence relation which is ergodic, then R has cost less than n, so I fix n greater or equal than 2. If and only if there is an action, so of my Fn on x mu, so R is on x mu. X mu is a standard probability space. So it's if and only if there is an action of the free group on x mu such that R is equal to the equivalence relation attached to this action. So it's really the set of all x, gamma x, where gamma belongs to the free group. And the action is not free. So, all right, so here I guess, I mean, everyone now is familiar with PMP equivalence relations. So these are the equivalence relations which arise when you have a group acting on a standard probability space and you look at the equivalence relation being in the same orbit. You can also give an axiomatic description of this, but this is not really important for me. But there is this thing about cost. So I mean, I don't want to define cost in this lecture. So if you've never seen it, you can just take it as a definition of cost. So equivalence relations of cost less than n are exactly those which come from non-free actions of the free group on n generators for ergodic equivalence relation. All right, so the basic question I want to ask in this talk is how non-free can this PMP action be made? So, I mean, the initial hope is that you would have, I mean, by considering somehow the degree of freeness of the action, maybe you could get some new invariants of equivalence relations. Maybe you have some for which you get that the action cannot be as free as some other equivalence relations. But I mean, as we will see in this talk, I don't have any statement of this kind. So all the notions of non-freeness that we will see, they can be asked for this free group action. Okay. So so the main point of my talk will be to do two things. So to make this non-free business very precise, give you several definitions of non-freeness for free group actions. And the other thing will be to relate this to these full groups of equivalence relations that I will discuss in a moment. Okay, so for now, we are working with the free group on n generators, and we will review various non-freeness notions. All right. So, by the way, feel free to stop me at some point if something isn't clear. I mean, I did not give many definitions because I think you are all familiar with this topic, but if it's not the case, feel free to interrupt me. All right. So one interesting thing when you move to non-freeness, to non-free actions. So yeah, maybe I should remind that, okay, an action of gamma on x mu is free. So this is in the measured setup. So we are looking at things up to measure 0. So one way of saying this is that for almost every x in x, and for all non-trivial group element, gamma x is different from x. And from this, you get that actually the map, a better way of thinking about this is that the map which takes gamma and gamma to gamma acting on x is injective. All right. So now said in this manner, you see that, I mean, this map that I wrote here, it's equivariant with respect to the left action of gamma on itself and the natural action that I have on x. In particular, when I have a free action, I see that the action on each orbit equivalently, I mean, almost every orbit is isomorphic to gamma acting on gamma by left translation. Okay. So, I mean, the main point of most of the non-freeness notions that I will describe is to actually look at the action on each orbit and ask that it is somehow far from being free. So here is first notion. So one way of being non-free, or I mean maybe first way of being non-free, you just note that Fn is not amenable. In particular, if Fn is acting transitively so I have a transitive action which is an amenable action, then this action is not free. So let me maybe remind what is this notion of amenability for transitive actions or for actions on discrete sets, if you prefer. So Fn acting on Z. So Z for me will always be a countable set. is amenable? Well, if there is a sequence Fn, so this is just the usual Fellner definition. You have a sequence of finite subsets of Z, such that for every gamma in the free group, gamma Fn symmetric difference Fn divided by the cardinality of Fn, this goes to 0 as n tends to infinity. Okay, and the point is that, well, the natural action of the free group on itself is not amenable because the free group is not amenable. So if you ask that the action on the orbit is amenable, then definitely you cannot have a free action. Okay, so one definition of Fn acting on X mu, let's say very non-free, is for almost every X, the action of Fn on the orbit of X is amenable. Okay, so this is one way of being a non-free action. Okay, another way, so a second way, is to ask, is this notion of high transitivity. So gamma acting on a set Z is highly transitive. So HT. If, well, it's, well, not only transitive, but transitive at every level. So there are different ways of stating this. I will first state the most, let's say, intuitive way of saying this, I think. So whenever I take x1, xn pairwise distinct, and also y1, yn pairwise distinct, there exists an element of gamma such that for every I from 1 to n, I have that gamma xi is equal to yi. Okay, so your action, not only it is transitive, but it is really as transitive as it could get. But I also want to mention that there is an other equivalent definition that I will come back to at a later point. So whenever I fix a finite subset of Z, I can consider the setwise stabilizer of F. So let me write it as gamma F and say that this is the space of gamma in gamma, such that gamma F equal F for every F in F, for the pointwise stabilizer. Of F is acting. So this is a smaller group, but it's still acting transitively on the complement. Okay, so it's fixing these points of F, but outside of it, it's acting as richly as one. So it's a small exercise to check that the two definitions are equivalent. Okay, and so these actions have recently received quite a lot of interest after a work of Hull and Ozin, where they show that, if you know what that means, essentially what they showed is that every acylindrically hyperbolic group admits a faithful highly transitive action. So you have to take care of a finite kernel for this statement to be true, but essentially that's it. So I won't say more about this notion, but of course, when you have a free action, then it's very far from it, because it's a simply transitive action. So once you fix where one point x goes, one point x1 where it goes, you have no choice for where the other xi's are going. So this is okay. This is, again, let's say that also a PMP action now of Fn on x mu is very non-free. If for almost every x, Fn acting on the orbit of x is highly transitive. All right, so now we have these two notions. So first was amenability, second is high transitivity. And now, okay, so these two notions are purely in terms of the action on each orbit separately. So now I want to tell you about a third way, which this time is completely. I mean, it's a measure theoretic notion. I mean, it's a notion of measure preserving actions. But you can still define it for set. So let me first give the definition for actions on set. So gamma acting on the set Z. So here I don't want the action necessarily to be transitive. I just view Z as a discrete set. So this is the notion of total non-freeness. So the action is totally non-free. So you can already see in the name that it has something to do with contradicting freeness. So, and I should say that this definition is due to Verschick. This action is totally non-free if the map, which takes a point x in Z to the stabilizer in gamma of x, which is by definition the set of gamma in gamma, such that gamma x is equal to x, this map is injective. All right, so why can this be seen as a negation of freeness? Well, when you have a free action, all the stabilizers are trivial, so this map is never injective unless you're just acting on a singleton. Okay, so okay. So free actions are never totally non. And so what's the measured notion? Well, you just ask that this is injective, but you may have to restrict to a full measure set. So now a measure preserving action gamma on x mu is totally non-free if there is x0 in x of full measure such that the map x maps to the stabilizer of x is injective on x0. All right, so I mean, stated like this, it might seem a bit, I don't know, not artificial, but why would you care about such a thing? Well, one very good reason to care is that what you get. So if gamma acting on x mu is TNF, Then, so the stabilizer map is injective, but now let us remember that. So let me write this down first. So this is injective up to measure 0. But it is more than an injective map. It's, I mean, it's always equivariant for the gamma action on the space of subgroups of gamma. And this action is the action by conjugacy. I mean, all I'm saying is that the stabilizer of gamma x is gamma subgamma of x gamma inverse for every x for every gamma. And now, so what you get from this, by pushing the measure mu forward via the destabilizer map, we get a gamma invariant probability measure on subgamma. That is what is also known an invariant random subgroup, IRS, of gamma. And what is the point? So this is always true to every measure preserving action. You can always associate an IRS. And note that when the action is free, this IRS is just the Dirac measure on the trivial subgroup. But I mean, in general, when you're looking at non-free actions, the associated IRS of the action is an interesting invariant of the action. And the point is that when the action is totally non-free, this IRS is conjugate to your initial action because of the injectivity. So this IRS is isomorphic to gamma acting on x mu when gamma acting on x mu is totally non-free. All right. So this gives you the fact that, in particular, the action you started with is actually, I mean, it's a very nice action. It's you can view it as an action just on the space of subgroup of gamma by conjugacy. Okay. So let me now maybe state the first relevant result towards what I will state. By the way, I completely forgot to mention, so I will scroll back up. Sorry. So this is joint work with Alessandro Carderi and Damien Gaboriau. Okay. And so, yeah, the first theorem I wanted to mention is due to Lewis. It is that it says that, I mean, if I look again at this statement of Gaboriau, here I can actually ask that my free group action is actually not only not free, but actually totally non-free. So, theorem, take R ergodic of cost less than n, then there is Fn acting on x mu, totally non-free, such that R is equal to R Fn acting on x mu. All right. So so this is good. But so there are several points, so further questions that you can ask. So one question that you can ask is, so you want to have, you're talking about non-free action. So first, can you also get, let's say, non-freeness? Can you also get, so gamma, I mean, Fn acting on the orbits highly transitive and amenable for almost every x. Okay, so this is a strengthening of the non-freeness. And also, can you get a faithful Fn action? So we really want to know that we are not having, for instance, an action of a quotient of Fn, which is a natural thing to ask. All right, so let me first comment on the second thing, the faithfulness, and give you one more definition. So yeah, I'll first give the definition for an action on a set, a transitive action on a set. So yeah, sorry, I forgot to write transitive. And I should say that this definition is it first appears in some paper of Preo, I think. Although I'm not completely sure that it did not appear somewhere else before. So an action is highly faithful if, so you kind of take of a dual point of view to this notion of high transitivity. And really the first definition. So we had something which was happening for every n. And here we want that whenever we take gamma 1 now, gamma n non-trivial element of the group, there exists x in x such that gamma I of x is different from gamma j of x for every I different than j. Okay, so here the definition is, yeah, I should have said first, so for every n, whenever I take n elements, n non-trivial elements, so I should take them, sorry, stated like this. This is not correct. I should rather say that all these guys are pairwise distinct. I want that they send x to a different point. Okay. And I mean, so this is a kind of dual to high transitivity, and the point you have really a geometric way of understanding this, which is important, which is that so suppose that gamma is generated by a finite symmetric generating set X, S, sorry. So gamma acting on Z is highly faithful if and only if for every positive radius one can find a copy of the R ball of the Cayley graph, of the S Cayley graph of gamma inside the Schreier graph of the action. All right, so you have to think a bit about it to see why this is equivalent, but it's true. So yeah, just to be sure, everyone is okay with this notion of Cayley graph and Schreier graph? No question. Okay, so again, high faithfulness mean finding copies. I mean, here for the free group, this means that I will really find in my Schreier graph copies of arbitrarily large balls of the Cayley graph of the free group inside my Schreier graph. Okay, so let us say that gamma acting on X mu is highly faithful if for almost every X, gamma acting on gamma dot X, so gamma acting on the orbit of X is highly faithful. All right, so now I can state a kind of intermediate result which I obtained some time ago. Take R ergodic of cost less than n. Then there is an action of the free group on X mu such that R is the equivalence relation associated to this action. And so the action is totally non-free, highly transitive on every orbit, on almost every orbit, amenable on almost every orbit, and highly faithful. All right, and now I can state the last piece that I need to, piece of notation that I need to set up. So actually, Fn is dense in the full group of R. So this I need to tell you a bit more about this and tell you how it interacts with the conclusion that I've made. So, okay, let's talk a little bit about full groups. So, given R a PMP equivalence relation, its full group R is, well, the set of, the group of all T from X to X, measure preserving bijection, such that for every X in X, well, X and T of X are related. In other words, the elements of the full group, they are measure preserving the bijections, which preserve each orbit. Okay, so really an element of the full group, you can think of it as acting by permutation on each orbit. And really, I mean, for this group to be separable, you need actually to look at things up to measure 0. So you quotient out by this, where t is equivalent to t prime if the measure of the points where they agree, or where it's either where they differ, is equal to 0. And so what's very nice about this group is that you can endow it with a complete separable topology. So topology induced by, I mean, sorry, if I say complete, I want to say that I have a metric, sorry, du given by du of st is the measure of the set of x in x, such that f of x is different from t of x. Okay, and so the fact that this is a metric comes precisely, I mean, that I have separation really comes exactly from the fact that I quotiented out by this equivalence relation. All right, so this is actually, and so this metric, one can check that is left and right invariant. In particular, group operations are continuous. So this is actually a Polish group. And so here are a few facts. If I have gamma, a subgroup of a full group, which is dense, then R is equal to the equivalence relation generated by the Gaboriau action. But actually, more is true. You have the following theorem, which for me was really kind of revelation. So by Eisenman-Glasner, they noticed that for almost every x, gamma acting on the gamma orbit of x is highly transitive. All right. So this is nice. This tells me that when I have a dense subgroup in the full group, automatically I get this hypothesis is this one comes from this. This is implied. Okay. And another thing that I observed is that total non-freeness is also implied by density. So so if gamma in X is dense, then you have this, and you also have that gamma acting on X is totally non-free. Okay, and so you get two things, and then you only need to, I mean, then of course, then you need to show something stronger. You need to show this density. But these two hypotheses, I mean, these two conclusions are then automatic. Okay.
Francois, could you say a few words about why density implies totally non-free?
It's basically because you see, I mean, you want to be able to separate points, and I mean, the thing is that in the full group of R, so a few words about the proof. So in the full group of R, for every A in X, there exists T in the full group of R, such that the support of T is exactly equal to A. Okay? And now remark that gamma acting on X mu is totally non-free if and only if the algebra the algebra generated by the supports of gamma for gamma and gamma, this is dense in the measure algebra of X mu, because this is exactly saying that up to measure 0, this is the algebra generated by these guys is exactly what you get when you look at the stabilizer map. When you pull back the Kloppen set, which says gamma belongs to this specific subgroup, you get exactly you get exactly the support of gamma.
Yeah, I see. Great. Yeah.
So, and then, yeah, using density, you can approximate actually any element of the measure algebra. So this density is not hard once you have noted this. Okay. Okay.
Thanks.
So now there's one more thing that I want to tell you, and it's not in our paper with Damien and Alessandro, because it's a property that we wanted to study a bit further. But so there's a very nice way of putting together these two notions. So this is due to Alessandro, Damien, and myself. Actually, when gamma is dense in the full group, so this is a new notion. So I will give it, one tentative name. We're not yet sure how to call it. So, but you have a full measure set such that the gamma action on X0, so X0 is gamma invariant, and the action of gamma on X0 is what we call, for now, it may change, and if you have ideas of a better name, please tell us, because we are not very happy about this one. So it's permutationally full. So what does that mean? Well, let me state it in the easier, give you the quick definition. Whenever I take a finite subset of X0, so I always have this pointwise stabilizer of F, which is acting on X0 minus F. And this has the same orbits as those of gamma intersected with X0 minus F. All right, so this is the definition. And the point is that this is really a version of, this is really a nice generalization of high transitivity. So why? Because, if you look, if all the elements of F are contained in the same orbit, then I'm just saying that gamma F in particular is acting transitively on the complement of, on the remaining part of the orbit. But this is much more general, because basically I'm also dealing, not only I can do whatever I want on a single orbit, but basically this is telling you you can do whatever you want on any orbit, but and you have just one constraint, is that, gamma cannot send points of a gamma orbit outside of a gamma orbit. So in particular, this definition can be reformulated as, if I give me finitely many, if you give me finitely many finitely supported permutations on finitely many orbits, then there is an element of the group gamma which acts exactly like these finite permutations on each orbit. So so it's a kind of a stronger, I mean, a strengthening somehow of high transitivity. But the remark to make is that this, I mean, permutationally full implies highly transitive on every orbit, and also totally non-free. So really, once you're working on this set X0, this full measure set, and you view it as a discrete set, you have both these properties automatically. And so, in particular, I mean, this puts under a common umbrella these two results. So, so this is nice. Okay, so now there is still one word that I haven't defined, which was in the title, which is this totipotent thing. So there are many ways of understanding it. And here I will try to be as quick as, I mean, to be quick. So I look at the space of infinite index subgroup of Fn. Yeah, I should put brackets here. So this is the space of lambda in Fn, such that this lambda is infinite index. So observe that when you have R PMP ergodic, so first, this is a closed subset of the space of subgroup of the free group, and one can actually show that this is actually the largest perfect closed set in there, but I don't want to spend time on this. So my point is that when R is PMP ergodic and R is equal to R of Fn acting on X, well then, for every element, almost every element, well, the Fn stabilizer of X, well, it belongs to this space. Okay, so it belongs to this closed set just because, I mean, it's the orbits are infinite. Okay. So, and now, what is the promised definition is that, I mean, gamma acting on a set Z, let's say now transitive action, is, so yeah, let's take this, sorry, for the free group on n generators. This is called totipotent if the set of stabilizers of element of Z is dense in sub-infinity of Fn. Okay, and notice that this is a single conjugacy class. So this is really a property that I can determine by just looking at one point, taking its stabilizer, and looking whether its orbit is dense or not in the space of subgroup, whether its conjugacy class is dense in the space of subgroups. So what is the point of this is that this definition very nicely generalizes two of the previous definitions that we had. So observe that if Fn acting on Z is transitive totipotent, then two things. It is faithful. It is actually, sorry, I want to say highly faithful. And second thing, it is amenable. So I won't have time to tell you why this is true in details. I mean, I won't have time to write it down, but let me just say how to interpret it. I mean, how to understand this thing in terms of Schreier graph. Well, I mean, an infinite index subgroup is just giving myself a transitive action of the free group over an infinite set. So now, what is totipotency? What is it telling me? Is it telling me that if I fix a ball in the Schreier graph of an arbitrary action over an infinite set, which is transitive, this ball will appear somewhere in the Schreier graph of my totipotent action. Okay, so the action, the action on Z. So you see now that, I mean, since the free action of the free group on itself is an action over an infinite set, then you get by approximating this action, this free action, you get this high faithfulness. And for the second one, you just need to observe that there exists an amenable Fn action over some infinite set. For instance, you can just build such an action by projecting your free group onto Z in any way you like, and then making it act on Z by translation. Okay, and so you see that, I mean, totipotency will imply this this amenability, because when you imitate the Fellner sets of this action, you will get Fellner sets for your initial totipotent action. So I now just have time to tell you our main result. I wanted to tell you a bit about the proof, but yeah, time is running out. So yeah, let n greater or equal than 2. Suppose R is ergodic of cost less than n, then there exists a free group action of, I mean, an action of the free group on n generators, which is, I mean, the corresponding copy of the free group. I mean, okay, let me state it this way. So R is equal to the equivalence relation associated to this action. And maybe if I call alpha the name this action, then I want to say that I have then a copy of the free group inside the full group, which is dense. And so alpha is, I mean, Fn acting on Fn.x is almost surely totipotent. All right, so I think that's the statement, yes. So, okay, so here again, density, it gives you for free total non-freeness on the one hand, and this high transitivity onto every orbit on the other hand. And this totipotency, it gives you for free these two consequences that were in my previous result, which were so high faithfulness and amenability. All right. And okay, I don't have time to tell you about the proof, but there is really a new ID, an important new ID compared to what I had done previously. So, and what I had done previously used the really, I mean, in what I had done previously, the first generator of the free group was acting freely. So there was no way to get totipotency because, I mean, you must be able to imitate actions where the first generators has some cycles. So there really is a new idea in order to deal with this first generator acting freely. And let me just mention that in Bowen's result, the fact that the first generator was acting freely was also crucial. I mean, he was his result uses a Baire category argument, but the Baire category argument is over actions where the first generator is acting freely. And let me just end by asking the following question. So consider the space. So let R ergodic of cost less than n. Then we can consider the space of alpha such that, so alpha action of Fn on X, such that R is equal to Rfn. And this is, you can show that this is a Polish space. And so the question is the generic element of alpha, the generic, sorry, element of this set. So I don't know, let's call it A curly A, as in our result. All right, so yeah, you need to make an assumption like this. I mean, you can't just look at the space of all Fn action, which give you a sub-equivalence relation. This is too large. So you really need to make this restriction a priori to get a genericity result. But this is not known, and I mean, really, we basically don't know anything about this set. I mean, for basically any of the consequences that we got, we don't know if it's actually a generic property in this space. So okay, so I think I will end here. Thank you very much.
Yeah, let's thank Francois. Yeah, so very nice talk. Well, if you have a question, you can just unmute your mic and ask. Yeah, I like this question at the end.
Yeah. Yeah, our construction is very specific. I mean, yeah, it's a concrete construction, but yeah, I mean, the downside is that, yeah, we're far from getting a genericity result.
How do you get around this this idea that, you know, like as you said in previous proofs, the first generator acted freely? How do you get around that?
So basically, what we do is really about. I mean, it's already difficult in the hyperfinite. I mean, you can already see this difficulty in the hyperfinite case. So let me maybe quickly sketch what happens for the hyperfinite case. So this is X, and the point is that we will actually do something a bit weird, which is we'll take a smaller x0, x0, and what we will show is that you can find a T0 in the full group of R restricted to x0. So, okay, here R, take it hyperfinite ergodic. And So this is just a statement about the ergodic hyperfinite equivalence relation. There is a guy like this, and there is a U such that for every n, the full group of R restricted to x0, it contains as a dense subset the following. So the group generated by the T0 conjugates of U. Sorry, not of U, but of U to the n. All right, so this tells you, I mean, and here something is allowed to vary. I mean, I is taking values in Z. Okay, so you look at all the conjugates of U to the n, and you get a dense subgroup. Okay, and now what we do with in the remaining part is basically we try to make the action totipotent. So we have here, let's do it with F2. So first, the second generator, U. So here I have my T0 and I have my U doing this. And now I want to extend to the whole space. So first, I extend U so that it exchanges some part of x0 with the complement of x. So notice that when I do this modification, if I now do, I mean, if U also does that, then U squared is just my original element U squared in here. So I did not modify this property somehow. Okay. And now the point is that we try to, so we want to make the action totipotent at the same time. So what we do is we have U doing this, maybe, and then we have this largest set X1, where we kind of construct an action so as to get the Schreier ball of some prescribed action. And in here, so T and U, yeah, sorry, this is probably too sketchy, but they have finite orbits. So I extend T0 by making it act on this now new set, disjoint from X0, so that I get a kind of a piece of Schreier graph of some action. And I do this countably many times. And each time I start with U doing something like this. And then so I glue my things together. And I mean, the point is that really this is a big modification to both T0 and U, but T0 on X0 was, I mean, T on X0 was not changed. So its conjugacy action on X0 is completely unchanged. And U to the n, the point is that if I take n very large, U to the n, since U had only finite orbits in this all of these spaces, after some time, U to the n, the support of U to the n will be very small, and it will be contained in a very small set. Okay, I mean, except for okay, it also has some support on X0. Okay, but on X0, it is doing the thing that I want. Okay, and the point is that now you have to check it. It's a bit surprising, but this property. So if I'm given some epsilon positive, I want to approximate an element of this full group. I make the support of U to the n, let's say, smaller than epsilon over 2. And when I conjugate by T0, the point is that T0 will not move this support too much. So this will stay in actually a T0 invariant set of still small measure, so that you will be able to approximate your given element in the full group here. Okay, and once you've done this, you're basically you're good to go, because I mean you have some argument to say that once you get the full group of of this guy here, you can, because X0 was of measure large enough, and because the saturation of X0 is the whole set, you actually got everything. So yeah, this is probably too sketchy, but I mean, yeah, you can check the paper for a more a better picture than the one that I drew here, and hopefully a better explanation.
Okay. Okay. Well, are there any other questions? Okay. Well, let's thank Francois again.
Thank you.
Thanks for a very nice talk.
Thanks.
Yeah, okay, I guess that's it for today. Next week we're having Ben Hayes, and that's it for the for this mini series. Okay.
Okay. Thank you. Bye.
Bye. Thanks again.